Hello there. This is going to be a video on the Helicycle interface chassis that I designed. I've got two left, which I would love to sell to two Helicycle builders. Hence the need for this video. The idea behind this thing is to have a common place where all of the cabling can interconnect, sort of the grand central station of my wiring. And so I designed this chassis to fit between the rails that attach the instrument pod. So it sits right at the bottom of the instrument pod, and it has a number of connectors and relays on it, so everything can be modular. The instrument panels, the chassis wiring, the cyclic grip, all of these things have individual cables that plug into this one common chassis. The other reason is to have a common ground point for all of the shielded cables. That's very important to keep noise down. And so that's why I did it. So the way I have this thing laid out, obviously if you bought one of these from me, you can do whatever you want. But the idea was, starting in the upper left, J1 and 2 would be all of the external sensors and actuators and lighting that are not part of the instrument pod themselves. So anything going out to the frame, to the engine, to the transmission, all of that stuff comes in on J1 and 2. J3 is the cable from the cyclic grip. So all of the switches on that grip come in on J3. J4 is the lower instrument panel. J5 and 6 are the upper instrument panel. So you can see if I wanted to pull out those panels and take them into the shop, I just have to unplug those connectors and they come right out. On the other side, top to bottom, some of these things I've stopped selling, but I'll go through them anyway. You can always put whatever you want there. J7 was going to be the connector where my master caution and warning annunciator and my crew alerting system processor board connects. All of the UMA indicators that I sell have external alarms. Everywhere there's a red line, there's an alarm. All of that stuff goes out through J7 to that processor board, which then drives warning lights and various alarms. The next one was a fuel totalizer processor. The standard Helicycle only has one fuel probe and it's in a lower tank. So your indicator shows full fuel until you've burned off something like 6 or 7 gallons out of the top tank. Maybe it's only 5, but still it's like a third of your fuel's been burned, and your indicator shows full fuel. So I never did like that. So I added another probe in the upper tank and designed a totalizer. I have a video on that you can look at if you're interested. And so it takes the inputs from both of those probes, combines them into one composite output, which drives the fuel quantity indicator. So all of that stuff goes through J8. J9 was a great idea that never quite came to fruition. It was going to be a transmission torque indicator, so that one's unused. The next one was my rotor alarm processor, which produced RPM alarms for low, high, and red line. But as with a lot of Helicycle items, third-party items that people try and sell, there's just no profit in it. It's just not worth it to do this stuff. It's just too much work. So I've stopped making those. but that's what that was for. And then J11 was the communication headset. So I have this separate little cable. It's got a DB9 on one end that plugs into this chassis. The other end is a jack where my headset plugs in. And then that fans out and would have gone over to, let's see, where would that go? I'm not quite sure where I went with that, but anyway, it would end up going to the communication VHF transceiver. And that's how that works. And then all of the shields, as I say, would go into the chassis, get grounded to the chassis in turn is grounded to the frame. So that's the idea. In case you don't like my design, but you think you'd like to make your own, I had these manufactured by a company called Protocase. Their software is free, and here's a screenshot of the chassis as I designed it. Actually, this is a previous version. It only has 2 relays. So this was part way through the design process, and then I moved things around, added some more relays. But it's a photorealistic process that you use, and it's great fun. They have a minimum quantity that they produce because of all the setup involved, and so hence the reason for making this video. I needed 1 of them. I ended up with 3. So if you like the idea, there's 2 more sitting here ready to go. This is what they look like. All the wiring, or most of the wiring, goes on that top plate, so it's pretty easy to get to. And then the tricky part is you've got to interface to the 3 connectors on the box itself, and you can see those on the left side of the box. That's the cyclic grip and all the external stuff going out to the frame, the engine, and the transmission and the clutch. So you have to interface that stuff to the top plate. That's a little tricky, but can be done. This is what the top plate looks like when it's populated with all the D-sub connectors and the relays. You'll notice everything has a latch to prevent connector coming loose in flight. Not shown in this picture are the latches that clip over the top of the relays, and they attach to the relay sockets to hold them down. The other thing to note is all of these connectors are either different sexes or different number of pins. So it would be very difficult to swap these around and plug the wrong connector into the wrong mate on the chassis. And the DB9, actually DB connectors come in a number of sizes: 9, 15, 25, 37, and 50. And of course male and female. So what I've done is tried to use either different sexes or different size connectors, especially if they're adjacent, to minimize the chance of getting something swapped. Here's the bottom side of that same plate, and in the middle there between the relays you see the bus modules that I use, and they clip into that DIN rail that you see there. Here's a section of the interconnect diagram for the chassis for my design. Over on the left are all of the cables that are coming to and going from anything that's external to the instrument pod. So lighting, engine sensors, fuel probes, clutch switches, all of that stuff is coming in on the left. And I mentioned the bus modules. you see all these guys here. All of these are going off to bus modules. And so typically, what I'm using those for, obviously plus 13 volts. If something needs plus 13, it's supplied from a bus module. And ground returns all go back to bus modules. And then there are other smaller groupings like lighting sync for strobe lights. And I'll show you how that works. There's two flavors of these modules. They're pretty nifty. And there they are. So the ones on the left here, these guys, are 1x12s. So everything, every pin on these is bused together into one bus. And I typically use those for plus 13 and battery returns. These guys over here are 4x5s. So this is one bus with 4 pins. This is a second bus, which is isolated from that one. Here's the third bus, fourth bus, and the fifth bus. So these are good for things like I said, for sync, for your strobe lights, things like that. Here is one of those 4x5 modules that I mentioned. So the top row, A, B, C, D, is spare. It's always good to leave room for expansion. The next row goes from my clutch switch, and so when the clutch is fully engaged, it then fires off my Hobbs meter and starts that ticking over, and also lights a panel light to show that the clutch is fully engaged. The third row is strobe sync, and so that goes to tail, left and right strobe lights. The next one is a cyclic grip switch, which goes to my start fuel solenoid and my igniter. And the last one is overflow from one of my plus 13 bus modules. I ran out of room and needed some more. So that last 4, those are plus 13s. Here's one of the 1x12s, and this is battery return. So basically everything here is going to go back to the negative terminal on the battery. So all of this stuff gets combined and sent back to the battery by these two lines down here. And I've doubled these up because I want to minimize voltage drop. So depending, what the load is, if all of these things are doing something at once, the load could be enough that it's worth adding another battery return line just to get the IR drop down a little lower. These are the D-sub connectors and EMI back shells that I'm using to get in and out of this chassis. You're looking at the end of the chassis, the back facing the rear of the ship, and this is where all of the external stuff comes and goes that is not contained inside the instrument pod itself. And again, I've used 3 different size connectors so that you can't get these backwards. The bottom one is a DB25, the middle one's a DB37, and the top one's a DB50. Again, you can see the clips that secure these things in place, here, here, and here. This guy here, which is not attached, goes to my cyclic grip, and then the upper 2 take all of the inputs and outputs from the lighting, sensors, and actuators all over the ship. You can see that each one of these has an EMI back shell, and a strain relief. And in here you can see the strain relief has some sticky back foam tape that acts as a cushion so that I don't damage the wires going in. All of the shields, as I mentioned, are all terminated inside that chassis. And here you can see all these green wires. Those are ground wires from the shields. And I'm using these solder preforms to deal with that. And I've explained how to do that on another video. But basically the braid ends right here, and this green wire is soldered onto the braid. The green wire then goes to a pin, goes through the connector into the other side. When it gets inside, then it's grounded to the chassis. This is how I do that. So let's say this is a ground wire coming out the inside of the chassis. I just have a little loop and then it's soldered into one of these holes. This then, of course, is screwed onto the chassis, so the path is, from the pin through here down to the chassis, from the chassis to the frame of the ship. So that's how all the shields end up getting grounded. Here's another shot showing how these clips hold the back shells in place so they don't fall out. This tab right here, this piece, is part of the back shell. It's screwed in with this little screw and a lock nut. And it's hard to see, but there's an indentation on either side like that. And so when you take this clip and you push it that way, it snaps into that indentation, and that's what holds these in place. Now on commercial transport aircraft, military aircraft, you'll never see connectors like this. They all use circular mill connectors, which are designed for the purpose and can't possibly come loose. But in home-built and general aviation aircraft, you see a lot of D-sub connectors. So these are good. I don't think they're going to be a problem. But I have designed the wiring in the Helicycle so every single one of these connectors could fall off in flight and the engine will still continue to run, just in case. But there's no reason these things shouldn't work. As I say, they're used in general aviation and a lot of home built. Vans, for example, uses them. And they're certainly used on all of the avionics that Garmin makes, just to name a couple. So that's it. That's what that chassis looks like. If you're interested, contact me and I can sell you one of these along with all of the connectors, the back shells, the clips, the relay sockets, everything you need. So thanks for watching, and that is the end of that.